Then also from my side, hello to everybody, and a great thank you to the organizers for setting up this wonderful meeting and for giving me the chance to speak here. So as Harry just said, I have worked on coherent transport and mesoscopic systems for quite some time. And today I want to talk about these endeavors a little bit. I will start with a rather general introduction to coherent transport and scattering theory. And then I will talk a little bit about this specific work, which was done together with my former co-workers at Aalto University in Helsinki. So let's get started. Yeah, okay, so here's the outline for the next 1 hour roughly. As I said, I will do a rather general introduction. This is the first 3 bullet points here. I will explain a little bit what is coherent transport, what is scattering theory, and how do we describe the thermodynamics of these systems. The second part will be a little bit technical, so please bear with me. I promise that the amount of convoluted equations will decrease rapidly then in the second part, where I'm going to talk about the context of the specific work that I just described. Okay, so what is coherent transport? So let us start with a macroscopic system. If you think of a macroscopic conductor, we usually have in mind something like this here. And transport in such a system can be imagined roughly as sketched down here in the lower part of the slide. By the way, you can see my pointer. Can you?
Can you move it? Yeah, we can see it.
Okay. Yeah. So transport in a macroscopic conductor can be imagined roughly as sketched down here. We have some large system in the middle. This is coupled to some reservoirs at the edges. And we have these basically classical particles coming in here. And as these particles travel through the conductor, they undergo frequent collisions with each other, with lattice vibrations, with impurities in the material, all sort of things. And the typical distance that particles travel between 2 such collisions is the mean free path lambda. And typically in a macroscopic system, which is the order of magnitude of centimeters and the temperatures around room temperature, this mean free path is extremely small compared to the dimensions of the sample. And therefore, the transport in such system is a highly stochastic process and is well described by diffusion equations, Fourier's law, and so on. So that's transport in macroscopic systems, diffusive transport. Now, we may imagine that we pick this setup and we make it smaller and smaller, and at the same time decrease the temperature. What happens then is by decreasing the temperature, this mean free path lambda becomes larger. And if we make the sample smaller at the same time, at some point we reach a situation where the mean free path is comparable to the size of the sample. And that's the regime of coherent transport. So now we are down to spatial dimensions of a couple of 100 nanometers and at temperatures in the millikelvin regime. And then you don't have classical particles anymore, but instead you have wave packages that travel through this system. And in particular, the majority of these wave packages go through the system without ever undergoing some scattering event. And that's because this mean free path is now larger or the same order of magnitude than the size of the system. And that's essentially what can be understood as coherent transport. And that's a transport regime that can be very well realized in experiments. I'm showing here 2 snapshots of experiments that have been recently done. The upper one, the group of Heiner Linke, and the lower one with François Parmentier. And as I said, these systems have been studied for a long time. They can be very well controlled. Currents can be measured with relatively high accuracy. You can measure things like current fluctuations. So these systems are, well, very well accessible in experiments. Now the question is, why should we be interested in studying coherent transport, in particular from the perspective of quantum thermodynamics? Now what I will try to argue is, although these systems have been around for a long time and the theory behind that has been around also perhaps since 1980s or even earlier, these systems can still teach us a lot because they can be used as a platform to study current questions in quantum thermodynamics. For instance, what is the trade-off between entropy production and current fluctuations? What is the role of quantum effects for these trade-off relations? All of this can be addressed within these settings. Then you have scattering theory, which provides a comparatively simple and really transparent theoretical model for these kind of systems. And that's really a strength here in this context, because this theoretical approach is relatively simple. You can understand physical phenomena in these systems on a relatively basic level. And you have access to quantities, for instance, current fluctuations, that you could never calculate explicitly in a complicated system or more complicated system. And as I explained before, these systems are very well controlled and under control in the laboratory. So nowadays, a lot of these things that I will talk about can actually be measured in real life. And that's, of course, also an appealing aspect. Okay, so let's jump into that. I will talk a little bit about scattering theory now and how this theory is used to describe coherent transport. So here's the basic model. So we describe our coherent conductor as a multi-terminal system. At the center, we have some scattering region. That's the conductor proper, if you like. And then we imagine that this scattering region is connected to the external reservoirs, which provide particles and heat, via ideal infinite leads. It can be multidimensional. Here I will assume throughout, for simplicity, that these leads are so narrow that they can be treated as one-dimensional. Okay, so that's the basic setting. And now we are interested in currents. So we imagine a situation where we have the central scattering region, which may be subject to some magnetic field, connected via these ideal leads to the external reservoirs. Then we let the system relax to some steady state. And then we have a non-equilibrium steady state where particles and heat are flowing between these reservoirs through this scattering region. And we may imagine that we are able to measure the particle currents, for instance, in all of these leads. And if we would do that in a time-resolved manner, then we could construct a diagram that would essentially look like the one shown here below. So if we integrate up the instantaneous particle current in the lead alpha, which is given by the expectation value of some current operator, then we get the number of particles that is extracted from this reservoir in some given time t. And this will generally be a stochastic quantity, so you get fluctuating trajectories that look somehow like this, in principle. Now you can repeat this experiment over and over again for the same total time t, and then you get a distribution of the amount of particles that has been transferred during this time t. This distribution will have a certain mean value and it will have a certain variance. And if the t is large enough, both of these quantities are typically linear in time. So the mean grows linearly, which makes good sense. And we have a steady state, a constant current, and therefore we constantly accumulate particles in these reservoirs. But also the variance typically grows linearly in time. And these prefactors here in front of this scaling is what we call the mean current and the current fluctuations. And these are the quantities of interest for the next 45 minutes or so. So how do we calculate them? Well, in general, the rules are dictated by quantum mechanics. And what you have are expressions that look like this. You have to take the expectation value of some current operator, so the curly J is the current operator, in the Heisenberg picture at some time t1. This average is taken over all possible quantum states of this entire system with some probability distribution. And then you integrate from 0 to t, and then you wait long enough and divide everything by the total time. And you have a similar expression then for the noise, which, as I said, is the variance of this distribution, scaled with t. Okay, so now let's try to calculate these things. And the first step we take is we focus on a single particle picture. So for the moment, we ignore that this is a many particle problem and assume we have just one particle that enters this conductor via one of these leads alpha. And then, this particle is scattered here in this central region, and with a certain probability amplitude, will move out through any of these leads. And this process is described by scattering states. The scattering states, called here psi alpha, are solutions of the stationary Schrödinger equation, where E is here a continuous variable, because this is an open system. And now you have to apply boundary conditions to make them proper scattering states. And these boundary conditions encode exactly the situation that I just described. So if you look at the wave function, namely the position representation of the scattering states, you want that there is an incoming wave, W minus, just a plain wave, as you see that here, some normalization factor, only in one of these leads. And in all the other leads, you have outgoing waves, W plus, and they come with some complex weighting factors, and these are the scattering amplitudes. So SE alpha beta is the amplitude for an incoming particle in the lead alpha to end up in the lead beta at the energy E. Because the system is not driven, energy is a conserved quantity in this scattering process. Okay. Now comes the crucial step. If we assume, if we assume that these particles are essentially non-interacting, and that's the important bit here, we can move from the single particle picture to a many particle picture simply through the mechanics of second quantization. And that's done by applying this formula here. So you make your single particle current operator, which has this structure here. So it's basically the velocity. Curly P is the momentum operator of a single particle. Curly X is the position operator, and you evaluate that there's some position in the lead X alpha, which doesn't matter in the stationary state. And then you symmetrize this variable because P and X do not commute. So that's the single particle current operator. And now you move to a many particle current operator by second quantizing this object. So you calculate the matrix elements of this little j with respect to the scattering states. And then you introduce fermionic creation and annihilation operators with respect to the same scattering states. So these psi operators satisfy fermionic anti-commutation relations, these curly brackets here indicating the anti-commutator. And then you evolve this entire thing in time, which, as I said, if the system is non-interacting, and this is where this assumption actually enters, is a trivial thing. You just accumulate this phase factor here. Now, if you had interactions, this would be much more complicated. Because we assume it's all non-interacting particles, you get this elegant expression for the many particle current operator. Now, last step is you have to average these things. And to this end, you assume that your reservoirs are constantly in equilibrium. And then you can calculate these thermal averages just using the standard rule. A standard rule of thermal many-body quantum mechanics. So the average of such a pair of creation and annihilation operators is non-zero only if they correspond to the same scattering state, meaning the energy must be the same and the incoming terminal must be the same. And then you get this weighting factor here, which is just the usual Fermi distribution. So once you have all these bits together, you can now go back to this first box here and calculate these quantities. This is now really just a matter of bookkeeping, and it can be all worked out. And if you do that, you get these expressions for the mean currents. This is the first one, gives you the mean particle current. As you see, you have the scattering, the squared modulus of the scattering amplitude, and then the difference of the corresponding Fermi distributions. That's just the usual Landauer-Perturber formula. And then I hope you trust me that you can do exactly the same calculation for the energy currents. And what happens is you just accumulate an additional factor E here in front of these Fermi functions. You have the mean particle current and the mean energy current flowing in the terminal alpha in the steady state. The current fluctuations are a bit more complicated. But these expressions can be understood by dividing the current fluctuations into 3 parts, which I have done here. And the first one is d alpha is the classical, or better to say quasi-classical thermal noise. It's given by this expression. It vanishes in the 0 temperature limit, but it persists in equilibrium. So therefore, it's reasonable to call this the thermal noise, which stems from thermal fluctuations in the reservoirs. Then you have this R contribution, which is the shot noise. The shot noise is, first of all, a non-equilibrium quantity, because you see if all of these Fermi functions are equal, then this object is trivially 0. And it stems from coherence. And that is indicated by the fact that you have, in fact, a 4th order prefactor here in these scattering amplitudes. What does that mean? So if I come in the terminal alpha, I have a certain probability amplitude to end up in all of the other terminals. That's just quantum mechanics. If this was a classical particle, I would have deterministic transmission. So if I come in some terminal alpha with some fixed energy, I will certainly end up in one of the other terminals, meaning in such a situation, all of the scattering amplitudes would be either 0 or 1. And one can show that, although it's admittedly not obvious from this formula, but one can show that in this limit, the shot noise is exactly 0. And then you have this last contribution, which reduces the noise. And I should say that all of these contributions are manifestly positive. And you see the F comes with a minus, so this is a noise reduction, and this is what I will call the Fermi reduction. This is, in fact, a quantity that comes from the quantum indistinguishability of these particles, specifically from the Pauli principle in this case. So you cannot occupy the same scattering state twice. And that's the physical origin of this Fermi reduction here. Okay, so much for this. Now let's see if we can make this a little bit more interesting if we drive the system. So we may now apply some oscillating electromagnetic field to this scattering region, and then we have external driving, and our scattering processes are no longer energy conserving. But nevertheless, I mean, the theoretical framework that I just described can basically be adapted in a straightforward manner. This goes as follows. First of all, these general formulas for the mean currents and the current fluctuations are not altered by the fact that I now apply some periodic fields to the scattering region. But on the single particle level, the picture changes. So now you can no longer argue with a stationary Schrödinger equation, because the problem is no longer stationary. But because the driving is periodic, you have the Fluctuation theorem, which tells you that there's a complete basis of your single particle Hilbert space consisting of time periodic states that satisfy this equation here. And this quantity E is then usually referred to as the Fluctuation eigenvalue. It can, however, although also this is probably not obvious, be directly identified here with the energy of the incoming particle. That's possible because this Fluctuation spectrum, like the original energy spectrum, is continuous, and therefore you can construct a one-to-one mapping. So if you choose these states properly, you can directly identify the effective eigenvalue in this Fluctuation-Schrödinger equation with the energy of the incoming particle. Okay, now to make these solutions of this object, which is called Fluctuation-Schrödinger equation, proper scattering states, again, you have to apply boundary conditions. And that goes as before. You require that you have only one incoming wave in one particular terminal. And then you will have outgoing waves in all the other terminals, but now possibly with a different energy. That's why you have this sum. En is just shorthand for E plus some integer multiple of h bar omega. It is, in fact, on the technical level, at least the consequence of the Fluctuation theorem that you can exchange energy between the particles and the driving fields only in integer multiples of h bar omega, where omega is the driving frequency. Okay, so if you come in with some energy E in the terminal alpha, you have some probability amplitude to leave in the terminal beta with some energy which is altered by nh bar omega. And then, of course, the corresponding plane wave changes, and you have this additional phase factor here. And it's obvious, I guess, that this object here is periodic in time, and that ensures then also that the entire solution of the Fluctuation-Schrödinger equation is periodic in time. Okay. And now the rest goes through as before. You can now construct your many particle current operators as before. The only difference is you now have to take the matrix elements of your single particle current operator with respect to these time-dependent Fluctuation scattering states and these fermionic creation and annihilation operators, create and annihilate particles in the Fluctuation scattering state at the time 0. So these Fluctuation scattering states form an orthogonal basis of the Hilbert space at any time t. And now you have to pick some reference time, which is conveniently chosen as 0. And at this reference time, you construct this set of creation and annihilation operators, and then one can show that the many particle current operators given by this expression here. In the Heisenberg picture, that's why you have this phase here. Okay, and then as usual, because the system is non-interacting, well, no, because the scattering states are mutually orthogonal, you have the standard fermionic anti-commutation relations. Yeah, and thermal averages can be calculated as before, because at every time these scattering states describe beams of particles, essentially, because they are not normalizable, that originate from a particular reservoir, of which we assume it is in thermal equilibrium. You can calculate thermal averages with the standard fermionic rule. And now again, you can puzzle everything together, and you end up with this result. So you have expressions for the mean particle and the mean energy current, which look quite similar to what we saw before. It's perhaps not a big surprise. The noise changes, or the current fluctuations change, because you acquire an additional contribution. So you can still identify the quasi-classical thermal noise, shot noise, and the Fermi reduction, and these quantities have the same interpretation as before. But now you get an additional contribution to the current fluctuations that really comes from the periodic driving, and it is given by this expression here. And what you see is, if you turn off your driving field, the scattering processes become energy conserving. Therefore, these scattering amplitudes are non-zero only if n is 0. So if you pick up no energy during the scattering process, and then this entire object is 0 because you sum only over those scattering amplitudes for which n is not 0. Okay, so that was the technical part. I hope that was somehow understandable. And I will now try to discuss how we can do thermodynamics with these systems. Let's see how we're doing in time. Okay. Yeah. So the thermodynamics of these systems is actually constructed in a quite straightforward manner. The first thing is we have conservation laws. Particle number is conserved and energy is conserved. That means the energy currents add up to 0 if you don't drive the system. If you drive the system, the energy currents add up to 0 together with the power that you inject through the periodic driving. That's pi AC here. You can also verify these equations directly from the expressions that I showed on the previous slide. Then you have a first law, which can now be constructed in a straightforward manner from these conservation laws. So you have two work-like contributions, the AC power, just the power injected through the periodic driving, and the electric power that's generated by the transport process. This contribution arises because you're shuffling around particles between reservoirs with different chemical potentials. So some particles may travel uphill, others may travel downhill, and in total, you generate this amount of electrical power in this way. And on the other side of this balance equation, you have the heat currents that flow out of the individual reservoirs, and those are the energy currents minus mu alpha being the chemical potential of this corresponding reservoir times the particle current. Okay, so now you have a notion of work and heat essentially, or power and heat currents. And then you can immediately write down the second law, which requires that the heat uptake from the individual reservoirs divided by the corresponding temperature and then summed over all reservoirs must always be larger than 0. There's no entropy production inside the system because we are in a steady state, and everything that happens inside this multi-terminal system is a unitary process. There's no entropy production here. All the entropy production happens in the reservoirs. Okay, now you can reformulate these laws in the language of irreversible thermodynamics, which is then helpful if you want to do perturbation theory. To this end, you introduce a set of thermodynamic forces or affinities. For the particle currents, the corresponding forces are just the chemical potential differences here divided by some reference temperature. That's essentially the voltage that you apply to these reservoirs. For the heat currents, the corresponding force is the difference in the inverse temperatures. Again, T is some reference temperature, which you can pick arbitrarily. And then it is advantageous to introduce a third type of affinity, which is not standard. And this is what I will call the mechanical affinity, which is identified here with the driving frequency, essentially. Times h bar divided by t to make it dimensionless. But essentially, this third affinity is the driving frequency. Why does this make sense? Because you can now write the total rate of entropy production in this standard bilinear form. So this is the standard form of the entropy production for a steady state process in irreversible thermodynamics. This part here with the double sum, this is just the standard thermochemical contribution, which comes from heat currents and particle currents. And then you have this additional contribution that comes from the driving. And this can now be written as a product of a photon current and this affinity. So this is essentially the power injected through the periodic driving. And if you divide it by h bar omega, which is the energy content of one photon, you get something that you may call a photon flux. And then you have the standard bilinear form. At this point, we have not made any approximation. Yeah, this is still exact. I should say that this requirement that the entropy production becomes a bilinear form in the thermodynamic forces and the currents does not define the forces or the currents in a unique way. But these definitions will be useful in the following for the perturbation theory that I would like to apply to these systems. Okay, so that's basically about thermodynamics. Now question is, can we go beyond the basic laws of thermodynamics with these systems, and can we explore bounds on currents and dissipation that go beyond the first and the second law? Why is this useful? 2 points. There are many applications, but 2 points will be particularly relevant in what follows. One is that if I have a non-trivial bound on a quantity that I cannot measure directly in terms of another quantity that can be measured, I have a chance to infer information that I could not gather directly. For instance, if I could write down a non-trivial bound on the total rate of entropy production, perhaps in one of these particle currents, in terms of one of these particle currents here, I could get a bound on the total rate of entropy production by measuring only a single current, single particle current, which is much easier than measuring all the heat currents in the individual terminals, which can be done in some cases, but it's generally not trivial. The second motivation to go beyond the second law is that we may be interested in finite time bounds on the figures of merit of thermal machines, which can be constructed on the platform of these coherent conductors. So the standard example is, you know that a heat engine has an efficiency that's bounded by Carnot value, which is usually approached in some quasi-static limit, where your power output is basically 0. So if you want to make a statement about the efficiency of your heat engine at finite power, you need a finite time bound on these thermodynamic quantities. And that doesn't follow from the first and the second law, because essentially these 2 laws do not involve a time scale. So you have no chance to say something about power and efficiency, for instance. To this end, you need to go beyond the second law. Okay, so that's the motivation. Here we go. Let's start easily and first try to address these questions close to equilibrium. And as I said, I'm now doing a perturbation theory, which we call linear adiabatic response. So we assume that all of our affinities are small. For the thermochemical ones, this is straightforward. So we assume that the chemical potential gradients are small compared to the reference chemical potential, and the gradients in the inverse temperature are small compared to the inverse of the reference temperature. For the mechanical affinity is a little bit more tricky. As I said, that means, if we want to do a perturbation theory in this F omega, we have to assume that the frequency is small. So it's an adiabatic perturbation theory. And it's not immediately obvious what adiabatic actually means in these systems. Now, if you have a closed quantum system, you want that your driving frequency is small compared to the typical level splitting in your system. But here we have no level splitting. I have a continuous spectrum of the single particle Hamiltonian. So this notion does not apply, but you can still do an adiabatic perturbation theory. And the essential parameter here is delta E, which is the energy scale over which your instantaneous scattering amplitudes change significantly. So if I now freeze these driving fields, I could calculate these scattering amplitudes for the system for some fixed value of these fields V. And then I could plot them as a function of energy, or their real and their imaginary part, and I will see some variations. And these variations will happen on some typical energy scale, which is proportional then to the derivative of these quantities with respect to energy. And that's exactly what this delta E describes. So it's a typical scale. It's not some fixed parameter. Why is that related to adiabatic perturbation theory? Because one can associate this parameter delta E with the average dwell time of particles inside the scattering region. So that means if I talk about slow driving in these coherent conductors, I mean that these driving fields change only very slightly during the average time that a carrier spends inside the scattering region. And this criterion then translates into this condition on the affinity. Okay, so these are the assumptions that we make. And now we just expand our currents in these affinities. That's just first order Taylor expansion. We get some coefficients, and I have written this first order Taylor expansion here in this compact form with these compound indices A and B, which run over all terminal and thermochemical indices. So X is either rho for particle currents or Q for heat currents. And then you have this for every terminal. And then it may also be omega for the mechanical affinity. You get these linear equations. Now you can show by using, you can now calculate these coefficients explicitly using the expressions that I showed before. And then you can show that they have a couple of nice properties. You have an on-cycle Casimir symmetry. Because the system is driven, the reciprocity is recovered only if you also invert the time direction of your driving protocols. So on-cycle Casimir symmetry is usually derived, and also in this case derived from time reversal symmetry. And usually, if you have a steady state process, you just have to reverse the magnetic field to this end. In this case, because it's driven, you also have to reverse the driving. And then you get this symmetry between reciprocal coefficients. Then you have a fluctuation dissipation theorem. The object appearing on the left here is the correlation function between the current operators in equilibrium. So I showed you essentially the diagonal contributions of this matrix P for the particle currents. That's what we call the particle current fluctuations. But it's now clear that you not only can calculate correlation functions between the same current operators, but between all of them. And that gives you an entire matrix. And this matrix in equilibrium is exactly identical with the symmetric part of your matrix of kinetic coefficients or on-cycle coefficients. It's a standard statement of the fluctuation dissipation theorem. It's still not entirely trivial in this case, because we're not doing a completely standard perturbation theory, since we have this adiabatic element. We assume that the temperature and chemical potential gradients are small, but then we also have the slow driving assumption on top of that. You still recover this thing in full glory. Okay, and then using this linear expansion, you can write your entropy production as a quadratic form in the affinities, where the coefficients are your kinetic coefficients, and that tells you now that this matrix of kinetic coefficients, or the symmetric part of it, has to be positive semi-definite. Okay, so now let's see if we can go beyond the second law, and the answer is yes. So one now has to play around a little bit with these coefficients, for which we have explicit expressions, because, as I said, thanks to scattering theory, you can calculate everything explicitly here. And then you get these bounds on the total rate of entropy production. And they have exactly the form that I tried to motivate before. So n is the total number of terminals here in this system. And then you have this coefficient k, which is universal. So for particle currents, this is just T over 2h, h being Planck's constant. And for the heat currents, it is something that is a third order in the reference temperature, the base temperature of your system. And then here you have either heat or particle current squared. So what this relation tells you is, if I measure a single particle current in the stationary state that flows in one of these terminals, I can put a bound on the total rate of entropy production, a non-trivial lower bound, which I could get exactly only if I was able to measure all the heat currents in all the terminals, which is much more complicated. So you have exactly this advantage that you can now bound a quantity that's hard to determine in terms of a quantity that's easily accessible. That's what these bounds do. Derivation is not terribly complicated. It's essentially, as I said, playing around a little bit with these kinetic coefficients. The underlying principle, so what implies these bounds, is really current conservation. So you know, whatever these scattering amplitudes are, they encode the entire information about the scattering region and the periodic driving. But whatever they are, they have to satisfy these unitarity conditions, which follow from the fact that time evolution in quantum mechanics is represented by a unitary operator, and they imply also that current conservation and all these things. And that's essentially all you need. So you use this relation, and then you get this bound. Okay, now let me briefly show now what you may do with these bounds. As a first example, I have this quantum generator here, which was suggested first here in this paper 20 years ago as an example of an ideal quantum pump. And this works as follows. So you have your two reservoirs, and in the middle, your scatterer is now just a loop, a one-dimensional loop, which is connected to these two leads via some ideal beam splitter here in the middle. This is an idealized model, which is insightful from a theoretical perspective. So what this beam splitter here that connects the loop to the leads, which then connect to the reservoirs, is constructed in a very particular way. So it does the following. If I have a particle whose energy is larger than h bar omega, then this particle comes in from the left lead, enters the loop, goes around the loop, and then leaves to the same side. So this beam splitter diverts the particle from the left lead onto the loop, and then if it comes back after going around the loop, it goes back to the lead where it came from. So now that's possible only for energies larger than h bar omega, but because we are applying a time-dependent magnetic field to this loop. In particular, specifically, we assume that this magnetic flux that goes through the loop increases linearly. As a result, there's an electromagnetic force around this loop that accelerates or decelerates particles. And here I have chosen the direction of this magnetic flux such that particles coming from the left are decelerated. And that means the particle now has to work against this electromagnetic force when it goes around this loop. And the threshold energy is quantized in this adiabatic regime. So if you have more energy than h bar omega, you manage to go around the loop once. If you don't, at some point, this particle will turn around, simply because it has now been completely decelerated to zero velocity. This is a classical picture, but it describes the physics effectively. Completely decelerated by this electromagnetic force, and then is accelerated in the opposite direction, so it goes back, and then this beam splitter diverts it to the other lead, and then it is transmitted, in fact. And particles coming from the left must now be, for consistency, all be accelerated, so they go around the loop no matter their energy. And that means, by the construction of this beam splitter, every particle coming in from the right goes back to the right lead. As I said, it's a toy model, but it has the advantage that things are easy to calculate. And now you may consider this as a generator that converts electromagnetic energy, the power that we put in through the periodic driving, in this case by changing the magnetic field, into electric energy by driving an electric current through the system. You can define an efficiency, which is then electric power divided by uptake of mechanical power from the driving fields. This object has this simple form here for this device. And then you see, if you do the calculation, that the bound that we had before is exactly saturated. Also, I should say, this is the definition of this efficiency, and this on the right is the upper bound that follows from the bound on entropy production that we just discussed. And then you do the calculation, and you get this result, and you see it's exactly saturated. That's a simple example, basically just to show that these bounds are tight. Now, you can do something a bit more realistic. You may, for instance, consider a quantum pump. So these devices operate in the way that's illustrated here on the right. You have two electrodes on top of your conductor. You apply some time-dependent gate voltages, which effectively create time-periodic barriers in your conductor. And in this way, you're now able to pump particles from one side to the other. Works in this cyclic fashion. Yeah, you lower the left barrier, you have some incoming wave package, and then it is stopped by the right barrier, and then you immediately raise the left barrier, confine this wave package, you lower the right barrier, and the thing escapes to the right. So that's a basic principle of a quantum pump, and these devices can operate at extremely high accuracy and therefore are candidates for making current standards. And there's a whole story about them on their own. And now what you can see from the bound and entropy production that we just had, you can bound the input that is consumed by this device. So the power that you have to input to change these barriers in terms of the number of particles that is transferred per cycle. And this bound, has this neat form that the energy uptake from the driving is bounded from below by h bar omega times the particle number transferred in one cycle squared. And then you can do the calculations, make some model for these barriers and calculate the scattering amplitudes and then your kinetic coefficients. And what you find is this chi here being some internal system parameter, which is essentially proportional to the distance between these two barriers. You find this dependence here of the number of particles q that are transferred per cycle on the height of these barriers. And then you see, if you compare the actual input, u divided by h bar omega as a function of q with our bound, that, okay, we are not exactly there, but we are at the same order of magnitude. Now, so the black line here is what you get from the direct calculation. That's the energy uptake from the driving as a function of the number of particles that flow in one period. For the red line, we have done a little bit of optimization, and this shaded area below is our bound. And again, this is a way of bounding a quantity that's difficult to access, because it's difficult to measure this energy uptake from the driving in terms of a quantity that you can naturally measure in such systems. Okay. Third example, just very briefly, because I'm also running a bit out of time. Quantum motors. This is a setup that was suggested by these people here in the group of Felix von Oppen a couple of years ago. This is essentially the reverse of a quantum pump. So you now assume that the varying potential inside your conductor is generated by some movable mechanical degree of freedom. You may assume you have such a little wheel here with charges on top of it. And as this wheel rotates, these charges move by close at the surface of this conductor, thereby generating potential barriers inside. And if I now generate a particle current inside the conductor by applying some external voltage, I can drive this little wheel. It's like one of these pedal wheels, just here with charge and on a mesoscopic scale. And again, now you can go and bound the efficiency, because you have a bound on entropy production that's non-trivial. You get a non-trivial bound on the efficiency, which here is defined as the mechanical output power, so really the motive power of this little wheel, divided by the uptake in electrical power. That's bounded by 1 by the second law. And in terms of our new bound, it is bounded by this quantity. J rho is the particle current, delta mu is the voltage that you apply. And now you can do the calculation, and you see again, V is the amplitude of these barriers here. Shaded area is our bound. The red line is what you get from the calculation. And again, there is some gap, but we are at the same order of magnitude. And again, this is a situation where you have an easily accessible quantity like this particle current, which then gives you information about quantity that's difficult to access, like this efficiency here, because you can essentially not really, well, it would be difficult to measure the motive power of this little wheel. Okay, so this was basically some illustration, and now for the last 10 minutes, I would like to talk a little bit about how these things generalize to situations that are beyond the linear adiabatic response regime. And specifically, I would like to talk about thermodynamic uncertainty relations. And to this end, I should probably explain a little bit what thermodynamic uncertainty relations are. So just very briefly, in a nutshell, where all of this started is with time homogeneous Markov jump processes. That means you have some network of states. This is perfectly classical. You have classical transition rates between these states, and you write down some master equation, which describes on an ensemble level stochastic trajectories where your system jumps between these states. And now you can go and count the transitions, for instance, from state 1 to 2, and the transitions in the opposite direction. And then if you add up these jumps, you get a number of net jumps from 1 to 2, which corresponds to an accumulated current in the system. Now, to make this a little bit more physical, you may, for instance, assume that, and that was the original thought behind that, this state network describes a biomolecular system, like this little biomolecular motor here, which has some internal states. And we may assume that in one of these transitions between these internal states, this little motor rotates by one step. And that means that the current corresponding to this transition would be proportional to the distance that this little motor has traveled if you put it on some little track, or the number of revolutions that have occurred there if it is fixed to some plate. So that's the basic kind of system that was first considered. And now what is remarkable is you can prove that any current in such a system for any possible transition and its fluctuations bound the total rate of entropy production that occurs in this process. So you have this remarkable relation, which is valid arbitrary far from equilibrium, P now being the fluctuations of these currents, J being the mean current, sigma the total rate of entropy production, and Kb is Boltzmann's constant. This holds for any time homogeneous, meaning not driven, Markov jump processes that satisfy detailed balance. Detailed balance meaning that the ratio of the transition rates between two states, forward and backward, is equal to the entropy production that occurs in the surrounding reservoir during this transition. And it is for steady states and for isothermal processes. But apart from that, it's super universal and it's valid arbitrary far from equilibrium. And now you can use this bound, for instance, in this context of this biomolecular motor to measure, for instance, the revolutions of this motor, and then from the mean number of revolutions and the fluctuations, you can infer the total rate of entropy production. And again, you can put a non-trivial bound on the efficiency of this device, which you could not measure directly because the input here is a chemical quantity. It is the number of ADP molecules that is consumed per revolution, essentially. So that was the basic starting point for this business of thermodynamic uncertainty relations. And since then, it has become a big topic in stochastic and quantum thermodynamics, and there are many generalizations of this, and a lot of work has been done over the last years. I should say these original bounds have been discovered by Barato and Seifert here in this paper, and then proven by Gingrich and co-workers a little bit later. And as I said, since then it has become a really big business, and I'm not going in all the developments here. I apologize for everybody who's not mentioned at this point. But instead, I basically jumped directly into the question that I would now address at the end, namely, what can we learn from coherent transport in the context of these thermodynamic uncertainty relations? And I have three aspects that I would quickly like to discuss. One is inertia and time reversal symmetry. So this original setup was for an overdamped situation where your system has no inertia, essentially. It was, of course, completely classical, so there was no coherence. Quantum indistinguishability didn't play a role. and there was no periodic driving because all of that was in a steady state. There are generalizations, meanwhile, of this relation for periodically driven Markov jump processes and also for open quantum systems, but now I really want to focus on this coherent transport situation. Just a brief recap. This is now the reason why I showed these convoluted formulas at the beginning. Please remember that we could decompose the current fluctuations in these four contributions coming from thermal fluctuations, coherence, reduction via the Pauli exclusion principle, and reduction via the periodic driving. So this is the essential physics of what follows on the next slide. These four contributions of the noise determine how we can write down thermodynamic uncertainty relations for coherent transport. So let's start with the quasi-classical regime. Quasi-classical here means we are in a low density regime. The fugacities of our reservoirs are small. Therefore, then the particle density is small, and Pauli blocking is essentially irrelevant. In fact, one can show that these Pauli blocking factors, or this Pauli reduction, Fermi reduction of the noise, is of second order in these fugacities. And therefore, if this fugacity is small, we may throw them away. Also, I consider a stationary situation here, so there's no periodic driving. And then it's relatively straightforward to show that if there's no magnetic field, and you have a direct symmetry between, if there's no magnetic field, then your scattering amplitudes are symmetric as a result of time reversal symmetry, and then you immediately get this bound. If you turn on the magnetic field, something interesting happens. You still get a thermodynamic uncertainty relation, sigma again being total rate of entropy production, P current fluctuations, and J mean current. But you have to pay a price, and you have to pay a price in terms of a numerical factor. So this bound is no longer 2, but it's now some irrational number, which is close to 8/9. This can be found by direct optimization within this direct minimization of this term on the left-hand side within these systems. So this is quite interesting. Should also say that I have set KB to 1 now. So there's no Boltzmann's constant anymore. But that's for quasi-classical systems. The same bound cannot be true for systems that operate in a deep quantum regime, where Pauli blocking actually plays a role. And this can be understood in terms of this simple model of a perfect energy filter. So what I have here is I have two reservoirs sketched here with their respective Fermi distributions, and I have some scattering device in the middle that lets through particles only in a small range of energies, which I assume is much smaller than the temperature, the base temperature of these reservoirs. So for this system, it's very easy to calculate the currents and the current fluctuations and the entropy production. And what you get is this expression here, which shows you that if I make the bias, which is proportional to this parameter f, if I make the bias large enough, then this ratio is exponentially suppressed, so it can become arbitrarily small. And that's a result of an exponential suppression of the current fluctuations through Pauli blocking. What you see is, if I make this bias large enough, then all the scattering states that come in from the left will be fully occupied. Those that come in from the right will be basically empty, simply because I have these Fermi-Dirac distributions here, and that leads to the suppression of the noise. Okay, but you can account for that, and then you have generalized thermodynamic uncertainty relations, which have this form, so you get this additional contribution here. You have to add the entropy production another time, so you now have a quadratic term in the entropy production on the left. These bounds are weaker than the original thermodynamic uncertainty relation, and they have to be because we know that they are not valid. But they are still fully operationally accessible. Yeah? So I did not have to introduce any quantities that would not be accessible in a real setup. So that's how you account for the Pauli blocking. And now the next step of generalization is, of course, you want to include periodic driving. and also this can be done, then you have to insert another factor here, which is proportional to the temperature of the reservoir that you're looking at. And then you have a perfect thermodynamic uncertainty relation for coherent transport, which now is valid for any multi-terminal system, any periodic driving protocols, magnetic fields, and arbitrary far from equilibrium. And it involves only operationally accessible quantities. That's, if you want, the most universal result that we got here. Now, you can go back to the examples and try and generalize the bounds that I showed before. For the quantum pump, you get this bound on the energy uptake. For the quantum motor, you get a bound that looks like this on the efficiency, where this factor phi here is some generalized Fano factor that involves the noise, the temperature, and the particle current. Yeah, so these are now the generalizations, if you want, of the bounds that I showed before for situations arbitrary far from equilibrium. Okay, I think I'm already over time, so it's time to finish. So I showed you that for these coherent conductors, we have a hierarchy of thermodynamic bounds on entropy production that go beyond the second law. In linear response, they have the simple structure. They involve only the currents and some universal coefficients. And then far from equilibrium, you have thermodynamic uncertainty relations that become weaker and weaker the more you modify the system. In the quasi-classical case, you have something that's very close to the original result. Once you include the Pauli blocking, you have to include an additional contribution, the entropy production. And once you add periodic driving, you have this temperature contribution here. Okay, what is left to do? Well, theoretical open questions, unification is one thing. These bounds do not collapse into each other if I turn on off the corresponding sources that modify this noise. So if I turn off the periodic driving, for instance, the lower bound does not collapse to the previous one. So these are, if you like, not really in a unified framework yet. Would be interesting to do the same for heat currents, for bosons. All of that I've shown was for fermions. Also, it's not yet clear to me if these bounds can be generally saturated and under what conditions. And then in a longer perspective, you would like to move perhaps away from this non-interacting picture, include interactions, and then also see if these bounds can be useful in experiments. That's it, I'm done. Sorry for going over time.
Oh, thanks a lot, Kai. That was really good. So I think we've still got time for questions. So does anyone want have anything?
Can I ask a question?
Yeah, go ahead.
Yeah, hi, Kay. Thanks for this very wonderful talk and wonderful set of results that you have shown today. So one question that I have is from your slide number 23, where you have this new bound for entropy production in terms of current square. Yeah, precisely. So I think I didn't get the entire point. Here now, this bound is expressed in terms of this reference temperature, as I can see. Right, and this reference temperature can be arbitrary, right? I mean, that's up to us what we choose, right? Because the current that you have, the current square is independent of this reference temperature. It just depends on the difference, right?
Yes, no, it also depends on the reference temperature. So this is the current is zero if the temperature gradients are zero.
Right.
But it does depend on the base temperature.
It does. Okay.
Which, in a sense, if you're a linear response, yeah, I see the point. But it does depend on the base temperature, and you see that from these expressions.
No, I think you're right, because you have multiple leads, and yeah, you're setting this T as reference, and probably this T factor doesn't cancel out from each of the contribution of the Fermi functions when you do linear response.
Exactly.
I think
yeah, exactly. That's it. If you expand that, you get derivatives of the Fermi function. They still depend on the temperature.
Right. Okay. Great. And the other question is from slide number 20, where when you wrote down the second law, the entropy production is, as you pointed out, is basically coming from the baths, the heat dissipated in the baths. But later on, when you write the entropy production, you also include the contribution from the electromagnetic field,
but
which
this
I
is,
thought,
yeah.
which I thought is a unitary source and should not contribute in the entropy production. So I was a little lost there.
Oh, sorry for that. So that's no, the entropy production is always given by this expression.
Right,
All what I
exactly.
do is I insert the first law here. No, I mean.
Oh, you massage this expression, yes?
Yeah, you basically massage this expression.
Okay.
You just replace the heat current by the
in terms of particle
energy current and the particle currents, and then you use the conservation laws. But it's the same.
Perfect. I got it. Sorry for that. Yeah, it's clear now.
Sorry.
Thanks.